The essential thing to take out what we have learned, I'll call it shadowing method, is a little motivation. Remember what we did and why we included Bernoulli map, a trivial map, as an example for field theory. This is a map. When you look forward in time, it has some number of branches. And in each branch, it had this simple stretching factor. So we had a law that said, roughly speaking, that phi n, my neighbor, only one neighbor, plus the stretching number, the slope of this map, phi of n. This, as it stands, would have only one solution, which would be phi equals 0. But then I issued an order that this difference can be an integer. And the moment I did this, it's a different map for every one of these branches, going from 0 to 1 to 2, etc. To find fixed points of this, look at the diagonal, that's where the fixed points are. And each one of these intervals had a separate fixed point, which depended on this order. And then when you think what this really is that what happens in this dynamics is that this grows too big and the central committee says, you're too high, I will force you to become normal height, which between 0 and 1, by issuing this order. And that will put me in one of these intervals. The basic idea is that this is a forced map. If you're just a linear map without this term, you have only one trivial solution, nothing of interest would happen. But by forcing it, I'm choosing different branches. And this thing is translating my field. When I put it on the other side, it turns out to be an integer part of a number which is larger than 1. So this is a translation in the field. So in shadowing method, we try to generalize this for a general nonlinear problem, not just a linear problem with integers. That's the inspiration for it. And the idea is that what this integer was doing was choosing a region in which every neighbor had a similar dynamics, used the same map. Now for nonlinear problems, what we'll do is we will choose this translation here, this guy, to place me into the neighborhood where I know I should be. So there are people who are 3 feet high and 7 feet high, and nobody in between. There's some variations. So there are pygmies and there are, Dutch or somebody who's very tall. And these are the options I have. So I will now, just like here, change my equation because you said that this is one equation for every value of the forcing term. I'm generalizing this to idea that, I have what we call now configuration space. All imaginable values of my field live in some state space manifold. But the ones that I want, the ones that belong to non-wandering set belong to different regions of it. The ones there'll be solutions, I can show that they belong to some regions which are disjoint. That's easy to do for repelling sets, like you saw in this case, and there'll be same thing for 5-4 theory. But in general, there are some things. It's finite number of them, so the non-wandering set is contained in them. So there's some alphabet. Let's say 0, 1, 2, 4, 5 cube, or maybe it's called A, B, C, to Z if there is some other example. And this region have a name. And now I want to have a a single representative for each one of these regions, which we will call phi hat of A. So he's in this region. There is another representative phi equals B. So this is like electoral college in the United States. There is a state, 30,000 people who live in Montana, let's say, and somebody imposes upon them a single representative called the elector. And what do we use electors for? To get some sense how tall people are in Montana or whatever other. What we now do is we construct a shadowing state. The central committee says, I want a lattice state where the fields on the sides of the lattice have a certain sequence of values. You can think of it as a vector or an array of symbols, M0, M1, M2. Easiest to understand if it's a lattice, Mn minus 1 on the finite lattice. And now I want a representative of this thing. And I'll use my electors to do this. So I want a state which, if this symbol was, something like A, I want representative from this area. If this was also A, I would also call it that. And depending on what the commando is, I get something. And I can draw this on a lattice. If it's easier for you to visual lattice state on a lattice, then this is something that there are lattice sites. And the field in this unknown example, has two values. So I have two electors. And if the field is in a region that's positive, then the lattice side just takes that value. But if it's negative, then I take whatever the negative value of the field is. And that's what I qualitatively want. But the problem with this is, of course, that this is not obeying the law, because the law is very finicky. This I call the shadow state. Why would shadow? Because we'll be able to improve it to become a better approximation to the true state using property of hyperbolic flows, which is called shadowing. But what's the problem with the shadow state? If I insert the shadow state, that's another conspiracy theory. Shadow state is not the true state. It's not a lattice state, because if I stick it into my law said blow myself up by a square compared to my neighbors, try to listen to the command. When I put this approximate state, which kind of has a shape of what I want because it's hopping between the regions in the way I want it, I add it up, I get an error. It doesn't add up unless it happens to be a fixed point, but everybody else is violating it. So this sum I'll call the forcing term that depends on particular commando, that central committee was it. And this is just a number. These guys I can assign or compute. Now, to me, it seems natural, and we can all agree on if you do that, there's a natural choice. The natural choice is, take this representative to be fixed points. In examples we're looking at, we always have fixed points. So this region has one fixed point, this region has one fixed point. It has lots of other points you could choose. But if we agree that we just take the fixed points, that everybody can understand. So it's fixed point, this one, that's just the value on this axis. F0 or F1 hat hat, depending on what command was, what M was for that thing. So I take these guys, and then when I add them up, I'll get a number, which is just by how much I evaluated the law. That's a very simple calculation in this case, because I have to know where I am and what my neighbors are. So I have to use only 3 symbols out of this whole string, no matter how long it is. And I get an equation that says that JM can be, very few things. If my neighbors are the same as me, then actually, this is fixed point equation. I obey the law. So this J of M, this forcing term, at my site will be 0. And same thing if both of my neighbors are also fixed point, then I satisfy the equation, so that'll be 0. But if I look at 0, 0, 1, so in the middle it's me, these are my neighbors. By time reversal, that's same as this. And when I compute it, it's very simple. You just stick these numbers in here. You get that number is the difference between the things. Let me call this minus A. And when I look at case where I'm 0, 1, 0, so I'm negative, my neighbors are positive, I'll get some differences of squares, obvious. And then when I look at 1, 0, 1 and 1, 1, 0 equals, get these numbers again, just with minus signs. And in other words, this only takes 3 values. 0 or A or B, or you can count them as 5 values, but there is very little computation you have to do to find what the violations. Now what I do is I will now subtract the 2 equations. So subtract the shadow state equation from the true equation. Now this is exact. This is exact. When I subtract them, I get exact answer. I'm not making any approximation. I'm just cleverly changing coordinates. And that's what I call M forced. So this has to do with my symbolic dynamics commands that came from the central committee. Remember, those commands were simply very, very rough. They say, go from this trench, jump into this foxhole, come back to this trench, go to this foxhole, come back, stay, 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 jump. These are the orders, right? So they're very qualitative. But the actual position of foxhole, I have to know the 3, 4, 5 significant digits to do this. So I force it by imposing what neighborhood every field should be in. I'm subtracting 3-term recurrences. In this one-dimensional case, there'll be 5-term. So I subtract these 2 equations. This is the original law. This is the table of violations by shadow state. Both of them are exact. And the difference is now in terms of deviations. This is the field that satisfies the equation phi. So this is part of a lattice state at site T minus my field, which is the shadow. It's in the same neighborhood, so it's shadowing like secret police, the real thing. And now there's an equation for deviations. So relative distance between the 2 states. And that equation is now very easy. You can always compute it. There is deviation of my neighbor to the left. There is a deviation of my neighbor to the right, or before or after me, if I'm in a queue. Then there's a term that had to do with these quadratic terms in this example. And it turns out you can write it as a deviation plus the shadow state t square. And they all add up to a source term m, which depends on the state. So just like for Bernoulli, for every instruction set that arrives from the general step, I have to compute this, but I showed it's a very simple computation. And this is now the equation I need to solve. It's exact. I made no approximations. I tried to explain this from the point of volunteers in wars. The idea is that when you have a nonlinear world and not just world of integers where our simple models live, is that within states configuration space of all possible values of the field, there's some regions which are covering regions for no wandering set, where we know we can partition space in disjoint regions. And this is a calculation for every nonlinear field theory. It's different for phi cube from phi 4 theory. It'll be different if you start doing Navier-Stokes or quantum electrodynamics. But the main thing is that if we can produce disjoint sets, then we can say that within every disjoint set, I put my agent, my informer, who shadows everybody in this set. And if I do this very persistently, so if you're trying to go someplace, but there is secret police, single agent in every region where you come, they'll have a very robust triangulation of what you're doing, where you've been and where you're going. And that's what shadow state does. And the only assumption is that I have a partition of possible field values on lattice sites into short and tall ones, or left-handed and right-handed, or whatever the qualities I'm using to distinguish them. But they have to be disjoint sets. And the shadow state is constructed by taking one agent, one elector or whatever in each region. And this is how I translate the commands from central committee, which are just, code of 7 letters or something, whatever the number of these guys are, to actual execution on the ground. I convert those integers into the actual foxholes by constructing the shadow state. And that's a set of, fields which are approximately the field you want to have, field value. But they're just real numbers. When you do this, you change your equation, just like we did for Bernoulli. What we did for Bernoulli, we used this translation. Now, because fields were integers, this was integer, this happened to be an integer, and we could literally use it as a symbol. The command was actually also the translation we need to do. Mm-hmm. Now, for the general nonlinear case, the original equation looks a little bit different because we're looking at deviations from shadow state. Now that has lots of advantages, but basic idea is they're supposed to be small because the regions, you are in a partition of the state space in smaller regions. So the deviation should be small. And in Bernoulli, this is true. We have to show it in particular case, but there'll be only one solution, one fixed point, even though this is nonlinear problem and this could have cotangents, exponentials. But in every neighborhood, there is a unique solution, unique fixed point, which is the one that corresponds to orders from the commander. But this is an exact equation, and solution when you solve it will be exact. How you solve it is now up to you. If you want to solve it like Bataille solved the problem, That's one possible way to do it. Inverse iteration method, what it did is, it took this equation, stuck everybody on the wrong side, and then took the correct route in this case. And you can use the same method in the new equation, because new equation is just as fine. Both are exact, but this one is the one that's designed for a given symbol block. This is a modified equation, which is exact because it just amounted to translation. This is just a translation of the field. You would do the same thing if you used inverse iteration method, but this term would be replaced by this source term. That's a calculation. And this should converge better than the original case. But now that you have this equation, and you know that in every neighborhood you have one iteration, my suggestion is solve it by any variational method, which is used to decrease the error of your initial guess. So in particular, Yuheng Lan has a new preprint in which he has a variational method that's suitable for very large dimension systems like Navier-Stokes. He tested on Navier-Stokes. And it's that kind of method that I think, or similar one, should be using to solve this. So, we just have to find extremum that satisfies this equation, and there are many ways to do it. So I want to do it, but now it's set up in a way that symbolic dynamics or qualitative dynamics is taken care of. And all you have to do is you have to just tighten it so it's correct answer. And there are many ways to do this. Now, the reason why I call this shadowing method is that once you understand it, you can improve it, because there is no reason why you should always use fixed points, which could be quite far away from the states you're interested in. If you have period 2 solution, period 3 solutions, you can put them into this machinery, and you'll just be shadowing better. What it means is whenever you have 3 symbols in your sequence, which coincide with the symbols of one of your period 3 solutions, you will use it as a shadow. And that's systematic. So it means that if I computed all orbits up to given length to go to the next larger array, I will use all the orbits that I already have to compute the next guy. Now, these are exponentially good because the hyperbolic systems have this property that to share many symbols in an area of the symbol plane or one-dimensional string, I have to be exponentially close, which means that my guesses will get better and better. And that's what Kai Hansen's article did, by looking at stable, unstable manifolds. It's in the same spirit, by improving it. There is a Turkish proverb that says, if you're on the wrong path, turn around, no matter how many steps you have taken.
Another question for the choice of these fixed points for the shadowing method. So like for 5-4, right, you have 3 fixed points. As you look at higher orders of periodic orbits, you get more and more of these non-wandering domains.
Each one of them owns a periodic point. Fixed points are just periodic points of length 1. So you encounter them first, and every next small domain has a unique shortest orbit, which is a periodic point. You can improve your calculation by saying, I have a better resolution of my counter set. I have better covers, so I can use that information. The convention is that the periodic point of period 1 for maps is called fixed point. The whole point of our approach is that we are only computing fixed point ever, because when we look at Bravais cell of some length, we are computing fixed points of that.
Mm.
So we always look, but you can interpret them as periodic points of some period because under translations, they visit each other under the length, the period of the Bravais cell. So you can call them periodic points, and fixed points are special ones, which are the shortest. Now, depending on the dynamical system, maybe there is no fixed point. Maybe the shortest point is period 2, etc. In the simple examples, we guaranteed to have fixed points. So that's a good way to start. You might decide there's some better way because you look at this domain and you would say, well, maybe I should choose a point in the middle of it rather than a fixed point. You'll discover that if you do this, the next time you iterate, your point is not within the covering set because you're only guaranteed to be in covering set if you're neighborhood of a periodic points. So it's hard to find safe shadowing states other than using periodic points because periodic points are there forever. So they're guaranteed to be in the Smale horseshoe, no matter how finely you resolve it. But almost everybody else gets thrown out. So that's the argument for using as representative the dullest of all points. Have no dynamics. I mean, they just sit there or they return every second time, but they're somebody you can rely on because they'll be there for eternity and they came from eternity. So they are there for infinite life. You don't need to do it. So for example, even the crudest shadowing, which is saying it's either positive or negative, you couldn't be cruder than that, is enough for that unknown problem. This is designed to be applied to any systems where you can partition the state space into the regions. Each region has a periodic point in it, shortest one that you can use as representative. So that's the idea of shadowing method. So you change your equations in a very simple way because it's just translating. So you're looking at deviations from shadows and the actual state. So it couldn't be simpler. And it doesn't look like a difficult calculation. You get a forcing term. Everything is exact. There are no approximations. You just get the equation in the new coordinates, new field coordinates for fields. And you have to design it for every symbol separately. But we already know this from Bernoulli and from CatMat. We're already used to that. So that's a straightforward generalization of what we already know.
But does the value of the error give us a hint as to how much we should change our guess? So it's like in the gradient descent method, the value of the gradient gives us an idea of like,
yeah. So, the simplest honest calculation you can do is you can use Newton method. In problems we are doing, you can just do this for everything we need to do right now because you have no problem of inverting 30 by 30 matrix if you're looking at state whose period is 30. So that's not a difficult calculation. What's good about using only translation is that orbit Jacobian doesn't change. So the orbit Jacobian of the computed from deviations is the same orbit Jacobian we had originally because orbit Jacobian is invariant under translations of coordinates. It's difference divided by difference. That's obviously invariant under translations. So derivatives are invariant under translation. So orbit Jacobian is the same. But it has to be computed, and you already know that. On each lattice state, you have to compute it separately, but you know that. And now I'm just saying there's an improved equation that exploits shadowing to find the lattice state itself. And it should be very robust because once you're in this lattice state, to get a wrong answer, you have to go, for example, from one field being positive to negative. And if they're well separated, that's a huge jump. Newton method will not go into the wrong. This improved equation has all the periodic solution as the original one, but it has one that's close to the zero in new coordinates, in deviation space. And the other ones are far away. it's hard to get to them because you have to brutally change the fields in it. It's very easy to fall into the right hole, and it's very hard to get the wrong one, because at every step globally, you're being forced to go to good.
These JT terms will have to be recalculated for every length of fixed points I'm trying to solve, right?
Yeah.
Because you can have a
Yeah.
new
So,
set of
right now, if you just have fixed point, it turns out you have a table of me and my neighbors. So it's a table of 3 symbols. And you calculate all the values. Turns out there are 3 possible values, one of which is 0. So there are like only 2 numbers you have to compute. So that's very simple. Now, if you are incorporating a solution of period 2, then you'll have to have a larger neighborhood. So you will have to look at 5 symbols or something. And again, the table will get bigger. There'll be more entries in it. To me, it looks like it's easy to automatize. Once you're given symbol sequence for each one of them, you get one of these formulas, and then you substitute the values. So this is done for all problems which have the same topology. This table is the table I gave you. Didn't say I have to look at a known at 6 or 200, just formula. So then you evaluate that table, and that's it. On a long symbol sequence, let's say 30.
Yeah.
But as I'm computing the J function, I only have to look at substring of length 3, me and my 2 neighbors.
Yeah.
So that's what makes it so simple. What I'm doing is, when I use longer periodic orbit, periodic orbit is like having a memory. If it's of period 7, to compute it, you have to know what happened 7 steps ago, if you think in terms of time. Longer and longer periodic orbits encode more and more information about the future and the past. When I step on a periodic orbit, I have to know the previous symbols to know where I'll step. A finite length periodic orbit belongs to a very small part of state space, a region. And this is a region of everybody who shared the same commands with me for a finite number of steps. After that, we all get divorced and go someplace, and we came from someplace. So it's a bundle of things. It's every given periodic orbit is a point. Every lattice state is a point in space. But it owns a neighborhood of everybody else who shared that set of lattice states for that window in time. Yeah. The shadowing says, I just use one representative for that window, and that will be exponentially improved deviation for that. So the price you pay is every orbit has its own equation. And that's what it did already. That's how it's sold by Bernoulli, etc. And but it's not a very high price, because you can tabulate this forcing terms. And once you tabulate it, you know how to compute them for any values of your parameters, as long as you have the topology of having 3 domains or something. The simplest solution is Newton method, which acts on the n-dimensional space for period n. So there is some Newton matrix, which happens to be orbit Jacobian matrix. So it's the matrix that we have to compute anyhow. Its inversion requires that you compute its determinant, that's whole Hill determinant. Yeah. So it kind of sits all variational method, the simplest version of it is kind of already built in everything we are doing. Now there might be just much smarter variational methods, because this is not practical when the state space get to be very large. It's okay when it's 30, but it's not okay when it's 100,000 or million. What we got from Bernoulli and temporal cat is that the symbols we're choosing it looked like a linear problem, but that's not correct. It was a different equation for every symbol. And because it's a linear problem, each one gave either one answer or zero answers. Yeah. So that continues. It just says that as long as there is some qualitative partition, what was done there was a translation, which is this integer m, the source term of force integer, which puts you in the right region. It picked out the right submap for your calculation.